So the next topic we really tackled was the global energy balance. And to start that discussion, we talked about the nature of radiation and energy and how energy really moves through the universe or through substances. And a lot of that has to do with electromagnetic radiation. And that exists on a spectrum. We're all familiar with visible light. And so visible light is just this narrow band in the middle of this much larger spectrum. On either side of that, the longer period waves, so longer wavelengths, are called infrared radiation, and ultraviolet radiation has a shorter wavelength. And that wavelength is directly proportional to the amount of energy contained in that wave. And so ultraviolet radiation is a higher energy wave. X-rays and then gamma rays are even higher. And so as that higher energy radiation encounters things, it becomes more damaging, right? Because it's higher energy. Infrared radiation is not generally harmful unless you get a lot of it, because as we know, infrared radiation transfers heat energy around through substances. And so what we said was that what we really said was that all objects in the universe, all material emits radiation. Okay, and so these are examples of infrared cameras. And so here's a dog and the world around it, and you can see that all of these things are emitting radiation. This is represented here as a false color spectrum, right, so that we can see it. But what this reflects here is that this house is warmer than the neighbor's house, right? It's this warmer colors, I assume, correspond to higher temperatures. But this is measured using infrared radiation because all objects emit radiation. The wavelength, or the amount of energy contained in that radiation, is directly proportional to its temperature, or rather inversely proportional. The higher the temperature, the higher energy waves come out, the shorter wavelength, right? And so this is pretty intuitive. There are lots of examples of this. An incandescent light bulb, not that there are very many of those around anymore, but that's a great example, right? As you turn an incandescent light bulb on, the filament starts to heat up. And at first you can't see it at all. If you had an infrared radiation, or I'm sorry, if you had an infrared camera, you would see that as the temperature heats up, it starts emitting higher and higher, or shorter and shorter wavelength infrared, right? Until eventually it starts emitting visible light. When it gets hot enough, it starts emitting visible light. If you continue to heat it up and it was capable of withstanding that, it would start to emit ultraviolet and then X-ray and then gamma rays. And that's how, that's one way that we produce X-rays, by heating up a filament very, very hot. Okay, and so all objects emit radiation. The Earth, or materials around us, generally emit infrared radiation, whereas the sun, because it's so hot, it emits mostly visible light, right? And so we started, we went from here into the global energy balance, but the really critical thing to remember here is that the sun is emitting visible light, and the Earth is emitting infrared radiation. Okay, and so those are distinctly different types of radiation, and they react with materials in different ways. So, and a good example of that is a window. In general, infrared radiation won't pass through a window. Visible light, however, does, right? Visible light passes through glass quite easily. That's why we can see through it. That's also, coincidentally, why a greenhouse works. Visible light comes in, it warms the surfaces inside of the greenhouse. Those surfaces emit infrared radiation back out, warming the air, but that infrared radiation is trapped by the glass because infrared radiation doesn't pass through glass. And so that's where the greenhouse effect gets its name, and we'll talk about in the next video exactly how that works with respect to carbon dioxide and other greenhouse gases.